Hi everyone, I hope you're all doing well. In this video, we're going to start a new chapter on aldehydes and ketones. So we have talked about aldehydes and ketones previously. We've even done some reactions with them, but we're just going to dive a little bit deeper into these functional groups. So we know that an aldehyde is a carbonyl group bonded to an alkyl group on one side and a hydrogen on the other. Ketones are carbonyl groups that are bonded to two alkyl groups. They can be the same or different. So some examples are shown down below of aldehydes and ketones. On the left, we have cinnamaldehyde, which is taken from the bark of cinnamon trees. So that gives us that cinnamon flavor. And then testosterone on the right is a ketone. So you can see that on the end there. And this is a hormone involved in the development of male reproductive organs. So let's talk about how to name aldehydes and ketones. We'll start with aldehydes. And let's look at a relatively simple aldehyde. So we've got a chain of carbons with our aldehyde there. So remember, the first thing we always want to do is look for the longest carbon chain. That's our parent chain. And for aldehydes, we want to make sure that that aldehyde is included in that longest chain. And because aldehydes have that hydrogen, they're always going to be at the end of the chain. So they'll always be at position 1. So we'll number this from right to left. All right, so we've got 6 carbons in our longest chain, so that is hexane, but we're actually going to drop that E and replace it with Al for aldehyde. So this would be hexanal. Now notice I didn't put a number in front of hexanal because it's understood that the aldehyde is at position 1. Let's look at a slightly more complex example. What if we have multiple substituents on our chain in addition to that aldehyde? Okay, so see if you can name this one on your own first. So you can pause the video and try this, and when you're done, you can unpause and we'll go over it together. So let's see what our longest carbon chain is. So we'll start at the aldehyde, work our way over, and then at carbon 4 we have 2 methyl groups, so we can just pick one of those to be our last carbon there. Okay, so it looks like we have 5 carbons in our longest chain. So that would be pentane, but we're going to drop the E and add Al. So pentanal. And then it also looks like we have a methyl group as one of our substituents at carbon 4 and a bromine at carbon 3. But looking at carbon 3, that is bonded to 4 different groups. So we have to figure out if that's R or S. All right, so let's assign priorities. So bromine would be priority 1. And then we have to decide between carbon 4 and carbon 2 as the second priority. So carbon 4 is bonded to 2 carbons and a hydrogen. The hydrogen isn't shown. And carbon 2 is bonded to just 1 other carbon and 2 hydrogens. So it looks like carbon 4 has the higher priority. All right, so going from 1 to 2 to 3, we're going to the right, so that would be R. And we also have an invisible hydrogen back here on carbon 3, but it is behind the plane of the paper, so we don't have to flip our assignment. It's just R. All right, we also have to alphabetize our substituents. So bromo will come before methyl. So this would be R dash 3 dash bromo dash 4 dash methyl. Pentanol or pentanal. All right, let's look at how to name ketones. So let's look at the following example. So let's find our longest carbon chain, but this time that carbonyl group is not at the end of the chain, it's in the middle. So we want to make sure it has the lowest position possible, or the lowest number possible. So it looks like it's a little closer to the right, so I'll start numbering on the right and make my way over. Okay, so we have 6 carbons in that longest chain, so that would be hexane, but we're going to drop the E and add ONE for the ketone. Now this time we do have to tell everyone where the carbonyl group is, or where the ketone is. So here it's on carbon 3, so we have 3-hexanone. Now there is another way to name this molecule, and it's kind of similar to how we would name an ether. So what we do is identify our chains on either side. So on the left we have a propyl group, and then on the right we have an ethyl group. So we would also call this ethyl propyl ketone. And we alphabetize ethyl and propyl. So again, very similar to how we would name an ether, but we can do this with a ketone as well. So that's also an acceptable naming scheme. All right. Now there are some aldehydes and ketones that have slightly different names than maybe what we would normally expect. So let's kind of go through some of those. So we'll just call these special aldehydes and special ketones. So they have slightly different names, or common names, I guess. So the first one is formaldehyde, and this is used as a preservative. So, there's only one carbon there, so typically we might expect this to be methaldehyde, but it's actually called formaldehyde. And this is carcinogenic, so scientists are trying to find different ways of preserving, for instance, bodies or other items. And then we have benzaldehyde. This is something that we did synthesize in one of our previous labs. And this has a bit of a sweet smell, like cherries or almonds. We also have, oops, I went back a slide. This is called acetaldehyde or ethanal. So there are 2 carbons in the longest chain, but more commonly this is referred to as acetaldehyde. And finally, if you have an aldehyde attached to a cyclohexane ring, this is called cyclohexane carbaldehyde. So quite the long name there. I barely fit it on the slide. Okay, so let's talk about some special ketones with different names than we might expect. So the first one is acetone. So we use this pretty often in the lab. It really helps to dissolve certain items. It can dissolve a lot of different things. So it has a nonpolar end and a polar end. So that makes it hydrophilic and hydrophobic. So it could really go in either an aqueous layer or an organic layer, for instance. And that's what makes it such a good solvent too. We also have a benzene ring with a ketone attached here, and it has a methyl group on the other side. We call this acetophenone. And then our last special ketone has two benzene rings, one on either side of our ketone, and we call this benzophenone. So these are just some names to be aware of. You can make flashcards for these names, but they're just more common names that don't really follow the rules we would typically go through. All right, so what if we had a molecule with multiple functional groups attached? How would we figure out which functional group to prioritize? Well, now that we've talked about most of the functional groups, there is a big priority list that you can follow. So here, if we start on the left, we can see that carboxylic acids have the highest priority. So let's say you had a molecule with both a carboxylic acid and maybe a ketone on it. You would prioritize the carboxylic acid over the ketone because the ketone is way down here. Now, what if you had a molecule with an aldehyde on one end and a ketone on the other end? Well, the aldehyde would actually have higher priority over the ketone. And you can see that you just kind of go through the list here. We're really starting with our carboxylic acid and ester at the top. Then we start getting into an acid chloride, amides, nitriles, aldehydes, ketones. Then we get into alcohols. Oh, the thiol got cut off here, but it's also on the other side. Then after thiols come amines, and then alkenes come before alkynes. And then we have alkanes, ethers, alkyl halides, etc. So if you're ever confused on what to prioritize, you can always consult this list. I'll try to post it on Canvas under study guides. But typically the more complex a group is, the higher in priority it is, for instance. But let's look at an example. So let's say we have the following, and we have to name this molecule. So what type of functional groups do we have here? Oops, sorry. So we have a ketone at the top. And then it looks like we also have an alcohol. Okay, so let's look at our chart. So ketones are here, and then alcohols are right below that. So it looks like in this case we would prioritize the ketone. Okay. So let's find our parent chain that includes the ketone. So we'll start numbering the ketone at 1 since we have a ring system here. And then 2, 3, 4, 5. So again, I numbered this so that all the functional groups have the lowest numbers possible. So our parent chain is cyclopentane, but remember the ketone is prioritized here, so we would end the name with O-N-E, cyclopentanone. And because we have a cyclic molecule, we're just going to assume that the ketone is at position 1 since we ended the name with ONE. Okay, and then we have to refer to that alcohol group. So it is a substituent in this case. So we're going to call it hydroxy, and it's at position 2. So we'll add 2-hydroxy cyclopentanone. However, notice that the alcohol group or the hydroxy group is on a stereocenter. So we have to indicate whether that is R or S. So feel free to pause the video and try to determine if that stereocenter is R or S. All right, so what would get first priority? The oxygen. And then what would get second priority? Carbon 1 or carbon 3? Carbon 1. And hydrogen's in the back, so we don't have to worry about that. So 1 to 2 to 3, is that R or S? It's S. Okay, so we can add an S to the front here. So S2-hydroxycyclopentanone. So again, if you have multiple functional groups on your chain, you can look at this chart to figure out which one should come first. Okay, now we're just going to do a little bit of review and then we'll stop the video. So we are going to look at how to prepare aldehydes and ketones. Again, this is review. We've seen all these reactions before. So let's say you have a primary alcohol. You can use PCC and then an organic solvent like dichloromethane, and that will give you your aldehyde. So now I'm going to give you a couple more synthesis reactions for aldehydes, and I want you to try to remember which reagents you can use to perform these reactions. So the first one, we have an alkene, and again we're going to turn that into an aldehyde. And on the bottom we have an alkyne. It's a terminal alkyne, and we're going to turn that into an aldehyde. So see if you can remember the reagents you would use for these two reactions. So pause the video, and then when you unpause, we'll go over it together. All right, so let's look at our alkene conversion to an aldehyde. What would we use for that? So counting our carbons, let's see, we only have 2 carbons in the aldehyde, and we have a bunch more than that on our alkene. So we probably need to split this in half, right? So that means we would need to perform ozonolysis. So we would first use ozone, and then we would use a reducing agent like DMS or zinc. What about our alkyne? How do we convert that into an aldehyde? So let's count our carbons. Our product has 1, 2, and then we'll just say that alkyl group is 3. So 1, 2, 3. Okay, so it looks like, let's see, do we have a Markovnikov or anti-Markovnikov addition here? Anti, because the aldehyde is going to end up on the less substituted carbon, carbon 1. So then which reagents would we use to perform this anti-Markovnikov addition? So we would use 9-BBN followed by hydrogen peroxide and sodium hydroxide. So if you want to go back and review these, the first reaction is, let's see, in section 12.10, if you have the third edition of the textbook, and 13.10 if you have the second. The second reaction you can find in section 8.11 if you have the third edition, and then 9.11 if you have the second edition. And the last one is in section 9.7 if you have the third edition, and then 10.7 if you have the second edition. But let me know if those sections are wrong and I can correct those. All right, so what about ketones? So how could we make a ketone? Well, there's several different options. So what I'm going to do is write out the different options, and you're going to try to come up with the reagent that you would use. So again, the first one, we have a terminal alkyne. In the second option, we have a secondary alcohol. In the third option, we have an alkene. And in the fourth option, we have a benzene ring. And then we're adding a ketone to it. All right. So pause the video, see if you can remember the reagents for these different reactions. And then when you unpause, we'll go over it together. All right, let's start at the first reaction. Again, we have an alkyne, a terminal alkyne, and we're converting that into a ketone. So let's take note of how many carbons we have here. So we have 1, 2, 3. Okay, and then let's transfer that over to our starting material. 1, 2, 3. And it looks like the ketone has been added to carbon 2. So would that be Markovnikov or anti-Markovnikov addition? Markovnikov addition, because that's the more substituted carbon. So, which reagents could we use here? So we could use okay. And then what about our second reaction? We're going from a secondary alcohol to a ketone. What could we use there? So we could use a gentle oxidizer like PCC, or because we're just converting this to a ketone, not an aldehyde, we could also use a strong oxidizing agent like chromic acid. Okay. But remember, PCC on a primary alcohol will stop at the aldehyde. If we tried to use if we tried to use chromic acid, getting all my reactions mixed up, if we tried to use chromic acid on this primary alcohol, what would we end up with? A carboxylic acid, right? So for primary alcohols, you want to use PCC to end up with our aldehyde. But if you're trying to convert a secondary alcohol into a ketone, You could really use any oxidizing agent, so it could be gentle or strong. So any of those are fine. All right, let's look at our third reaction. How would we create that ketone from our alkene? Well, I'm noticing the ketone only has 1, 2, 3 carbons there, or, well, the alkyl groups might be larger than that. And then we have many more carbon groups on our alkene. So it looks like we have to split this in half, similar to a reaction we saw on the last slide. So again, we would perform ozonolysis. All right, and how about our last reaction? How would we add a ketone to that benzene ring? And this is more recent. Friedel-Crafts acylation. So we need to add a leaving group to our acyl group, the ketone group. And then we need our catalyst, aluminum trichloride. So if you want to look up these reactions and refresh your memories, let's see, the first one is in section 9.7 if you have the third edition of the textbook, 10.7 if you have the second edition. The second reaction is in section 12.10 if you have the third edition, and then 13.10 if you have the second. Third reaction is in section 8.11 for the third edition. Oh, almost just wrote second below. 9.11 if you have the second edition. And the last one is in our previous chapter 18, chapter 19 if you have the second edition. All right. So next time we're going to talk about reactions that we can perform with ketones and aldehydes, and we'll go through some of those mechanisms. So I will see you then.